Oh,
Hey Alvin, how are you?
hello. Doing okay.
Yep. Did you have a nice uh 4th of July?
Yeah, it was solid. Just family. Yeah. It was fine. Like nothing crazy, but
Yeah, you're in like the Brighton area or whatever, right?
yeah.
Yeah.
It was okay.
Mhm.
Um, but yeah. Um, how about you?
Yeah, I went home to see family. My family lives in Long Island and it was good. It was good seeing them and um we had some like fireworks and firecrackers, which were pretty cool. Um and yeah, it was pretty nice. It was pretty nice. I got some nice rest and recuperation, so it's good stuff.
Yeah, always need that.
Yeah.
Um, okay, well,
hmm
I want to tell you tomorrow I'm taking my third exam
hmm
from Blueprint.
Got
So
Yep.
gonna see how that goes.
hmm
Um, but yeah, I guess today,
hmm
I just as always just want to go over more like practice problems
Yep.
that I'm having difficulty with.
Got it.
So, let me share my screen. Do you see it?
Yep.
Okay. So with this problem, it's there's only one question I have an issue with.
Okay.
So like I don't want to spend like a year reading this whole entire text, but like it's basically about extractions.
Yeah.
Um, and I've been having difficulty with like understanding them like fully
Okay.
as a like separating technique. So like um
So, what can you tell me about
you know
the? So let me just take a quick look. I'm gonna try to like read it fast, but it's
no
and
problem. Yeah.
understand stuff unless I read it.
Mm-hmm.
Okay. Okay. Then that. Okay. All right. You can go down. Okay. Did we talk about vacuum filtration before?
No, we have not.
Okay. What can you? Well, okay. I'm just gonna continue. Let's see.
Honestly, I don't think I can tell you a single thing about vacuum filtration.
You're saying you don't know a single thing about vacuum filtration?
I don't. I only know vacuum distillation. I was just thinking about it, and I realized I don't. I think that's something useful to also talk about.
What can
Or is
you
that the same thing?
what tell me what filtration is essentially.
Um, like separating small from particles from large particles.
So that could be something like perhaps size exclusion chromatography.
Yeah.
But let's talk about like the separation technique. So essentially, so you will have filtration, which is just imagine like a coffee filter or whatever. Um, like let's say that we have some filter that's that has pores in it that are small enough for the water molecules to go through, but they're too small for like usually like a solid or something to go through. So it's kind of like, like the coffee grounds or whatever, and you pour some
Hmm.
water through, the water goes through. So that's what filtration is. Um, and if we have this, for like a flask here, it'll whatever go through. But if we attach this to some type of hose thing that creates a vacuum inside of the flask, it just makes it so that more of that water gets through because you're creating like a vacuum in there. So it just helps that process go through better.
Okay.
So yeah, so filtration is just what you normally think of with a filter. Um,
Hmm.
so that's filtration. Now, distillation is, oh, I should also say that that filtration separates solid from liquids, with the solids getting stuck in the filter.
Hmm.
Okay. Now, separating, so most of the stuff that we end up doing will be separating liquids from liquids, and there's more than one way to do that. There's distillation, in which you take advantage of the different boiling points of the different
Yeah.
substances. All right. And, it's essentially like whatever you boil this thing, and then we have some column that we can put like cold water like around to kind of cool it so it can turn back into a vapor here and then drop into like a second flask. So like if I had, like, let's just say I had liquid A with like 100 C as a boiling point, liquid B with 140 C as a boiling point, you're gonna, after the distillation, you're gonna have the one with the lower boiling point, boil and then condense into the other flask, with the higher boiling point one kind of staying in that first one.
Hmm.
Okay. Now, how would you define boiling point?
It's the point at which something like um the external pressure is equal to the vapor pressure or something.
Uh-huh.
It's some Anki card I have.
Yeah. So, because the thing is, like, if you have like a water bottle or a closed thing, um, you're going to randomly have molecules of like the water or whatever liquid enter into the vapor phase and kind of like hang out up there on top of the liquid without needing, it to be evaporated. It just happens spontaneously. And if you have vapor, the vapor can put a pressure down onto the actual liquid itself. But if you, let's say you raise your temperature and you get to the point where your vapor pressure is equal to the atmospheric pressure, boiling happens. So,
Hmm.
yeah. So if I had like a little cup here or whatever, a container that's closed and it's full of this liquid, randomly particles from the liquid leave that liquid phase, oops, and hang out as vapor. And that vapor uh, presses down on the liquid, and that's what vapor pressure is. Um, and let's say it's open to the environment, that means that the pressure that it so okay, when it's closed, this is vapor pressure. When it's open, this is atmospheric pressure. And whenever these are equal, you get boiling. The thing boils. The liquid boils.
Vapor pressure is wait, I mean, doesn't like so vapor pressure is coming from like the the water vapor,
Huh?
it accumulates spontaneously,
Yeah, yeah. So,
and that's vapor pressure. And then atmospheric pressure is what again? It's the
oh, it's just the pressure from the atmosphere, from the like outside atmosphere,
okay.
right? Is like, what's the reason that if you have like, so like my cup here, I have water. Why is the water like not going like going up or whatever? Why is it staying put? Well, let me put it this way.
Um,
What if I was in
mhm.
space?
uh, I have no idea.
If I was in space, would this look like this? Would I be able to drink it like this?
There'd be no gravity.
Uh-huh.
It would come out of the container.
Yeah. So like not just because there's no gravity, because vapor pressure, let me see how I can put this. Okay. If you're swimming deep, like underwater, um, you experience a really high pressure. I guess like the deeper you go, right? Right.
Yeah.
And uh and that's because of gravity, because gravity is pulling everything towards that center of the earth. So if the gravity wasn't a thing, the oceans would not be, you know, low like that. They'd be all, just like in the air and stuff like that. So so gravity obviously plays a role, um, like it does in almost everything. But in like chem terms, we can express that as a pressure caused by, if you're underwater, it'll be caused by the water molecules that are on top of you that gravity is pulling down. Um, but if you're exposed to the atmosphere, that the gravity pulling down the air uh, causes there to be an atmospheric pressure that you experience. Um, and so that's what that atmospheric, yeah.
Is this like related to Henry's law or Raoult's law? I always mix those two.
Yeah, yeah, yeah. So like those, well, I think Rout's law could be like that partial pressure thing, but there's Charles' law, and yeah, the Rout's law is a partial pressure thing, but the other
Okay, I got you.
mentioning, like Charles' law, Boyle's law,
Gay ice Lussex. Gay
like
Lussex.
they all
There's like
come,
a third.
yeah, they all come together, thankfully, in the ideal gas law,
Right.
right? But it's really annoying if they ask a question like of specifically Charles' law or Boyle's law. But but yeah, no. So essentially, like, so okay, you know how people say hot air rises?
Okay. Yeah.
It's really that hot air floats on top of denser, colder air.
Okay.
So yeah. So basically, we have on top of us, I mean, we don't feel it, but air on top of us causing pressure. Um, and we can't really feel it, but a glass of water like this has atmospheric pressure pushing down on it, which is why this water is not, going upwards. But if I started to boil it, right, and I boil it such that its vapor pressure is equal to the atmospheric pressure, there's not going to be anything that is pushing down on it anymore, and it'll start to boil and go up. So that's that's just the idea of Well, that's what boiling point is. It's when that vapor pressure that's always there equals the atmospheric pressure. So there's nothing keeping the water or whatever liquid that we have down on this surface. Like the water should be going up and stuff,
Okay.
right?
So now about extraction. Or
Yes.
we're not there yet.
Yeah. So distillation takes advantage of the difference in boiling points.
Okay.
There's vacuum um distillation in which if the values for the temperature of the two compounds here are too high,
Yeah.
then vacuum filtration, what that does is it'll lower the vapor pressure, thus lowering the boiling point. So you can do
Yep.
distillation uh with things that have high boiling points. So that's what distillation is. Then there's chromatography, and chromatography takes advantage of the different affinities for the stationary phase compared to the mobile phase. So
Mm-hmm. Yeah.
yeah, so there's a variety of those like size exclusion, cation exchange, anion exchange, things like that. And then there's extraction, and extraction takes advantage of the different solubilities of something, right? So if we had like some nonpolar substance and some polar substance, and we have some, I forgot, it's like a Buchner funnel or something like that. You can have like, let's say, like the non-polar layer here, the polar layer here, and yeah, let's say that we wanted to add some polar substance, or let's just say substance A, which happens to be polar. If we throw it in this, it's going to be located in this polar or like aqueous part of the Buchner funnel, and that's what extraction is.
Yeah. I get a little confused. Like not really, but sometimes when it's like organic versus aqueous,
Yes.
I think it's a little better to refer to, yeah, like non-polar polar.
Yeah, because hydrophobic equals nonpolar, equals lipophilic,
Yeah.
all that stuff. Uh,
Yeah.
now, a lot of times you'll see the nonpolar organic layer on the top, but that is absolutely not required.
Okay.
Yeah. So these are the different types of, I mean, there's more, but I can just take a picture of my notes that I have with the rest of the types because there's like recrystallization, things like that. But the ones that you'll see the most will be like, well, recrystallization separates solids from solids, filtration separates solids from liquids, and then extraction and distillation and chromatography will separate liquids from liquids, and that's what you'll see mostly. You'll mostly see the separation of liquids from liquids.
Mm-hmm.
So, okay, let's see. If the or when the organic extract following reaction B, this
Yep.
is subjected to fractional distillation. Okay. That's I guess what what could that mean? Like what could fractional distillation mean?
I apologize. Hold on. Wait.
Sure, sure, sure.
We might be on the wrong question.
Uh,
This is it. This is it. Fractional distillation, though, I know. It's when the boiling point is the difference of the two boiling points is less than 25 Celsius. So you
Perfect.
add a fractionating column, and that's what helps it
Perfect.
separate.
Perfect. Okay. So let's
This
see.
was the one. Yeah.
All right. So we have um oops. So we have, okay, water is added to the concentrated residue from reaction B. Reaction B turns into 5N, 5O, and then 6N and 6O. And I'm going to guess water could participate in the hydrolysis, but let's see which liquid is most likely to be effective. Oh, so if they're saying an extract, all right, extracting the desired amine product,
Mhm.
amine product, maybe, is that, that seems like 6N. What would be effective? Okay. Well, we could do perhaps two things. I mean, ethyl acetate. Well, okay. Let me see. So we have methanol, which is hydrophilic, ethanol as well. Hexane is not. Ethyl acetate, I don't think that it is. Now, if they're talking about the amine product being 6N, we know that this amine is going to be hydrophilic and possibly produce hydrogen bonds. So my guess would be something that's also polar. But now, what would be better, methanol or ethanol? Um, oh, oh, here, maybe this.
Yeah, wait, so okay, first of all, I will say once again, it's because like we didn't
Zippy.
fully read through the passage. It's not A or B, it's C,
See, okay.
actually.
I was gonna check.
Yeah.
Okay, so
Um,
yeah, sorry.
but I'm not even gonna follow you. It's just because like we literally like speed ran through that passage.
Hmm.
But like here, so it says after concentrating the reaction solvent under vacuum, the amines extract into an organic layer, as
Yep.
we were saying, through liquid to liquid extraction.
Hmm.
Um,
So when I first looked at
oh
this,
wait, ethyl acetate. Sorry.
oh, okay,
I put N-hexane. I remember I put
yeah,
N-hexane.
because that's the most different, right? One, right? And
Yeah.
I was thinking about that, but yeah, okay. Let me see. Ethyl acetate. What is this? Liquid compound 6N. Concentrating the react, okay, extracted into an organic layer through this. So I guess that means that we want an organic um thing that it's soluble in. And the two ones that are, well, okay, we know about these. And then N-hexane and ethyl acetate are not miscible in water. But for some reason, ethyl acetate, well, I guess ethyl acetate could also be polar and very, very soluble here. So, um, show me that question stem again. So they're talking about, oh, I didn't even remember about the water being added. Okay. So yeah, so what's your take on this?
Um, okay, well, what compound, wait 1 second. It said the amines extracted into the organic layer. I just wasn't sure how to like what to choose between C and D.
Mm-hmm.
Um, I just wasn't sure they were different. Like,
Let me see here. Okay, so here it seems like they're giving us that the R. Okay, I think I understand it. So they're asking us what layer this would be in, right?
yeah.
That I circled. Now when I see this, it says that the R group here is a benzene, right? So that means this compound 6N is going to be this,
Mm-hmm.
where we have a hydrophilic amine group and a hydrophobic benzene group,
Okay.
right? So 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 the methanol and ethanol would work if it was, without that benzene ring, because
Mm-hmm.
it would be entirely polar. Um, and the N-hexane would work if it was just that benzene ring, because the benzene ring is nonpolar, but the amine is polar. So I think that they're using ethyl acetate to give you something that this molecule could be soluble in, because it has both the hydrophobic part and the hydrophilic part. So I think that would be um, what we can use here. Just because we have something that's both has, a non-polar segment like the benzene and the polar segment like the amine.
Mm-hmm.
Yeah.
Okay.
They're saying, okay. Water is, and then I missed the part where that said water is added to the residue of reaction B. So water is polar and tends to dissolve polar solutes and ions. So the second liquid needs to be an organic liquid that does not dissolve in water. And so it must be moderately polar. So so yeah, it's just going to be something that's moderately polar, aka has another molecule that's a good example of this is tyrosine, like the amino acid.
Yeah.
Sometimes people list tyrosine as polar, sometimes they list it as non-polar. But what's important is that you see that the benzene ring portion is non-polar, but the hydroxyl portion is polar.
Mm-hmm.
So for this, um, you know, just looking at this, I wasn't able to determine anything about it. But here they tell us that the R group is a benzyl. And in that case, that benzyl group would be nonpolar and the amine group would be polar. So we want to choose uh, a solvent that, is partially polar.
What about ethyl acetate makes it partially polar?
So if you go back to the drawing for it, you have the, uh, yeah. Was there a drawing for it?
No, no. I just searched it up, but
Okay. What do you,
I mean,
see?
I could see why it's polar. Like,
Uh-huh.
the C is double bonded to the O. You
Mhm.
have like the arrow going up. Um,
Yeah. Uh-huh.
and like, yeah, I mean, it's like a ester.
Yep.
So,
Yeah. And it doesn't so compare it to like ethanol and methanol and tell me how they're different mostly.
right. I mean, there's no OH on the ethyl acetate, so like it can hydrogen bond with itself,
Uh-huh.
and
Yeah, it's aprotic, right?
Mhm.
So the ethanol and the methanol, they're protic. They can be involved in the hydrogen bonding. But the ethyl acetate is not protic. It can't participate in hydrogen bonding, and it can't really give up or take a proton the way something like ethanol can do. Like if you had, I mean, like if you think about what could be like, how can we even form ethyl acetate? Well, you can take ethanol, right? We can then take a carboxylic acid to then the um give us that, right?
Yeah.
Turning it into that ester. So that ethyl acetate, oh, and then also, like, I guess, yeah, this would be like dehydration synthesis like this. So
Yeah.
yeah, so the ethyl acetate is not gonna is aprotic. It's an aprotic um substance that's both that's soluble in water but not that soluble. And so that's what works for this question, just because we have a soluble portion as the benzene and a non-soluble portion, which is the uh, amine part.
All right.
Yep.
Let's try another one. So, yeah, this is it. It's just the first question.
Yeah.
So once again, it's only one question out of all of them, but this is also like way less stuff going on. I feel like it just lists an extraction procedure.
Okay. They're asking which steps does this turn it? Okay, so
I
fluorine.
feel like it could be useful to kind of go kind of quickly through like what's happening each step, just conceptually.
Yeah, so we have a 2-gram mixture of fluorine, 2 naphthoic acid, diphenylamine. Uh, okay, and then it's dissolved in 25 milliliters of organic solvent diethyl ether, um, which would look like that, the diethyl ether part. Okay, separation experiment was performed according to the following steps. Step 1, the mixture solution was partitioned by pouring it into a separatory funnel containing 10 mLs of water, and the organic layer was extracted with 10 mLs of 1 molar NaOH. Okay. The aqueous layer was transferred to flask A, and concentrated HCl was added dropwise. When I see dropwise, I'm thinking titration, right?
Hmm.
Okay. To the flask until the pH paper indicated that the solution was acidic. Okay. Flask A was then placed in ice water to induce precipitate formation. Okay. The organic layer was extracted with 3 milliliters of 3 molar HCl. The resulting aqueous layer was then transferred to flask B, and 8 molar NaOH was added dropwise um, to flask B until pH paper indicated that the solution was basic. Flask B was then placed in ice water to maximize precipitate formation. The precipitates in flasks A and B were collected separately by vacuum filtration, rinsed with distilled water, and dried in an oven. And then the organic layer was transferred to flask C and dried by adding anhydrous magnesium sulfate to remove any residual water present. Organic solvent was separated from the magnesium sulfate in flask C by gravity filtration, okay, and the solvent was evaporated, yielding white crystals. Okay. Step 3, the purity of the 3 isolated compounds was analyzed by thin layer chromatography on silica plate. Silica, remember, is it polar or non-polar?
No idea. Not even gonna try.
So yeah, it's polar. Just
Okay,
write it down so you don't
got
forget.
it.
A sample of the mixture was spotted on the TLC plate as a reference in addition to the isolated compound. All right, a lot of stuff here that's kind of hard to visualize. Which of the following steps is 2-naphthoic acid separated from the mixture? So let's see. Um, the naphthoic acid has a carboxylic acid group in it, right?
So, do I have to know that it's a strong or weak acid?
Um,
If it's like one of the, or it doesn't matter. Just know that it's an
they,
acid.
did they say anything about that or?
Nope.
Okay, yeah, yeah. You don't, yeah, you don't need to know it. Um,
So it's just an acid.
yep. Like yeah, yeah. So it's okay. Um,
I know diphenylamine is a base.
okay. I'm gonna think that, let's see. Maybe so you make a mixture of all three, you throw it in with some water, and then you throw in some organic layer was extracted with that, and then aqueous layer was transferred to flask A, and concentrated HCl was added until it became acidic. So my guess is that this is not going to be the naphthoic acid because the naphthoic acid should be acidic to begin with and therefore titrated perhaps with a base, which I see perhaps here. Organic layer was extracted with the HCl, the resulting, so the thing that didn't get extracted out into the organic layer in the aqueous layer, okay, was then transferred to flask B, and then this was added dropwise until it became basic, and then ice water. So step 1, okay, so 2 is not even there. Step 3, step 4. 4 just says vacuum filtration, it doesn't really separate like uh these like liquid stuff. And then step 5, you're just taking the organic layer and you're precipitating it by adding this. Is it this? Damn.
One.
What am I? Okay, okay. Let's see what I'm doing wrong here. So I knew that it couldn't be step 4. I knew that it couldn't be step 5. So the only ones I was left with was step 1, in which they add the base, and step 3, they add an acid first. So I guess if we're looking to separate the acid, there shouldn't be a reason to add that acid first, because this should be then present in this acid layer, right? What was your um approach here? Were you able to eliminate certain things?
Yeah, I mean, when I ended up putting my answer, I think I put step three also, but like maybe if like step two, yeah. Well, I'd rather just go from the beginning. Like the mixture solution was so it was poured into the funnel containing water. Um,
Yeah, so I think so step one involves like just straight up throwing that thing in water and extracting it with base. Step three involves throwing in an acid and then a base. So if we're starting with an acid, which is what 2-naphthoic acid is, there's no need to do what they did in step three, which is add acid to it because it's already an acid. So step one um, pretty much displays that. They're not adding an acid, they're adding a base. So if we're starting with an acid already, then I guess it would make more sense for step one to be the step at which that 2-naphthoic acid gets separated.
okay, but look, this is what like my process thinking process is. I mean, they put the water in it. So then the two naphthoic acid mixes with the water. Now so in the aqueous layer, it's two naphthoic acid,
Okay.
and in the organic layer, it's fluorine. Now, how about diphenylamine? That would be in the organic layer.
Uh okay, let's see. So they started out taking all of this stuff and putting it in an organic layer, right?
Hmm.
So all of these products should be predominantly in that organic layer, the diethyl solvent layer,
Mm,
right? Um,
yeah.
so but so this first step one here, right? They added some water to the thing that's just straight up like an organic layer um to create like that new water layer. And then uh they so all of these things, my belief is that they're going to be in that organic layer, right? Because of what they say here.
Yeah.
So I'm going to think of all of them being in the organic layer, and then they add some water to create some aqueous layer, and then they added to the organic layer a base, and the base would take this 2-naphthoic acid that's considered non-polar because of the two benzenes. It'll deprotonate this, likely, giving you some charged substance, which I believe would make it more soluble in this water layer. So I think that's that first step there. And then in that second step, so like let's just write 2-naphthoic acid, 2Na, would move into that aqueous layer here. And then that aqueous layer goes into, whoops, into flask A, right? Aqueous layer. So we start off with the three things that they give us and an organic layer. And then in step one, we add water, and that creates the water layer. And then we add sodium hydroxide, which shouldn't affect the fluorine or the diphenylamine, but it should deprotonate the 2-naphthoic acid. And if it deprotonates it, it's going to have a charge. If it has a charge, it's going to be polar, you know, like even more than polar, because polar is a partial charge. So it's going to be a full-fledged charge. So when you add the base, you're going to get a charged naphthoic acid, which will then be soluble in that aqueous layer. And that's what happens in step 1. In step 2, we take that aqueous layer out and we put it into flask A. And that flask A should contain the 2-naphthoic acid. And then what they do to that is that they add concentrated HCl until it became acidic again. Because while it starts off as an acid, adding the base makes it its conjugate base, right?
What are you talking about? It though, like the tuna-proic acid.
Yes. So essentially, I'm just gonna,
Oh,
yeah,
okay.
yeah.
So, so step 2 is just getting it back into that old form. But I don't. I thought tuna-proic acid was polar at the beginning because it's an acid.
Uh, so it's just like the other two molecules that we talked about. Like it's hard to pinpoint if the entire molecule is polar or non-polar, but we can tell that the two benzene rings are the non-polar segment, and then the carboxylic acid is the polar segment. But when you deprotonate it, it's not just because remember, if something is polar, it has a partial charge. But if you give it a full charge, whatever properties something that's polar has will have those properties like even more so if it was a full-fledged charge.
Okay, so step 1
Yep.
becomes it gets that charge. It goes into the aqueous layer.
Yep.
Then it gets extracted into flask A, and then they add HCl, and so
Mm-hmm.
the it becomes its old form again. Old,
Yep.
yeah. So then you just have flask A, and that's it. It's by itself.
Yeah.
Then
Yep. Go on.
then you have the organic layer. That's what was left in like the that old funnel
Mm-hmm.
with the diphenylamine and fluorine.
Yes.
So what now? What does it mean to be extracted like with HCl?
You said
Like step 3, that first sentence.
oh, extracted with that. Oh yeah. So that means that the organic layer that remains, they're adding HCl to it, and when they add the HCl to it, it causes an aqueous layer to form again, right? So
That aqueous layer is going to be diphenylamine.
um the aqueous layer, okay, so I think that so let's see. So okay, they add some HCl, which creates an aqueous layer, and in that, I don't think anything would be in like fluorine or diphenylamine would be in there yet, but let me see. The resulting aqueous layer was then transferred to flask B, and then NaOH was added dropwise to flask B until it showed that it was basic. So, okay, so we're doing something in which we're adding the HCl to make it aqueous, and then we probably want something to get mixed in to that aqueous layer that they then add sodium hydroxide to. So my thoughts is that perhaps the diphenylamine uh could be interacting with that, but I'm not sure yet. Let me take a look at the other steps. So step 4, we have, oh, so flask A and flask B, we just collect them and find their precipitate. Okay, step 5 is when you take the organic layer and you add some dihydrous thing to remove whatever water exists. Then they precipitate that whatever would end up in flask C. So it's okay. So that should mean that flask A has that naphthoic acid. Flask B will have maybe the diphenylamine, and then flask C, maybe the fluorine. I'm not entirely certain of that, but uh,
Yeah, diphenylamine is in flask B.
oops, yeah. Wait, what's up? Oh,
Diphenylamine is in flask B.
yeah. Just because flask B, we're doing a thing with water, like we're creating another aqueous layer. So which one, fluorine or diphenyl, be more soluble in water? And again, they both have non-polar rings, but diphenylamine has an amine in it, and an amine can participate in hydrogen bonds. An amine would be, polar. So that will be in that aqueous layer. So it seems like what they're doing is they're mixing up these three things. And remember that extraction is all about taking advantage of the differing solubilities. So it's in terms of solubility in aqueous solutions, it's 2-naphthoic acid followed by diphenylamine followed by fluorine. So
Hmm.
flask A would be this, flask B should be this, and flask C should be this.
Hmm.
Um, yeah. So pretty tough here because they don't give us that much information. And I guess extracting something with something like organic layer extracted with 10 ml 3 molar HCl, like what does that mean exactly? Like, are you adding it to it? Are you like removing it? But what it really means is that you are adding a new aqueous layer. Um, Same thing with if you started off with an aqueous layer and then you added whatever, some type added the diethyl ether, then you would be creating an organic layer.
So
But
that's just something that I should be expecting to know for the MCAT. Like you could just create, I guess, an aqueous layer by just like adding an acid.
yep. Because the thing is that they're adding the acid and the base as aqueous. Like right here, you see it.
Oh yeah,
So that
yeah.
lets us know that they're adding some water. Um,
Okay.
but but yeah, if you can kind of take away that the 2-naphthoic acid is going to be the most like polar or charged, followed by the diphenylamine, lastly the fluorine, that can then help you out here. Uh, so like step 1 separates the 2-naphthoic acid. Step 3 separates the diphenylamine. So at least, when we were going through this, like I was thinking either step 1 or step 3, at least that can put us in the right direction because we know that step 1 and step 3 are creating the flasks that have the aqueous stuff in it.
Hmm.
So we know that step 1 and step 3 would be either the naphthoic acid or the diphenylamine. So we can kind of do a 50-50 at that stage.
What is the gravity filtration, real quick?
Oh yeah, it just essentially filtration, like with your filter. and whatever flask, and you just kind of let gravity do it. You let gravity do the work because it'll be, you know.
But isn't there gravity in vacuum filtration as well, or no?
Yep, yep, yep.
It's just
Oh, sorry. Yeah, sorry. So yeah, regular, like a regular filtration with, your filter here and then whoops, your flask here. It's only gravity that's pulling it down, right? Like if I have my drink again and I put like a filter here and I poured water through it, gravity is what brings it through the filter.
hmm.
But if I made the inside a vacuum, it'll lower that pressure on the inside and cause the water, like the water to that normally would go through kind of slowly if it was just gravity. It'll
I
go,
got you.
yeah,
Okay, so gravity filtration is gravity, vacuum filtration is gravity, but also vacuum makes it more efficient.
yeah. The only difference uh with uh with vacuum filtration is the example with lowering the vapor pressure. But yeah, I'm gonna take a picture here to show you. But yeah, you can show me the next one. Does this make sense now?
It's better. Definitely would like better.
Mm-hmm.
Quickly, if we could go over this one.
Yep. Okay. Oh, cool. This question like helps us out with the with the other question, the other one.
Yeah.
So that's good. Okay. Why? I mean, well, what do you? Yeah, walk me through what you think here.
No, my main question was just like explaining fluorine cannot accept H. Like, what happens when what if it would accept hydrogens, like protons? Like,
When you say,
what would,
yeah.
because this was the answer, and like, the only thing I was confused about, obviously, it's not hydrophilic. It's an organic compound, it's hydrophobic, remains a nonpolar layer. But then, like, what is so significant about the fact that it cannot accept H plus?
Oh, okay. Well, so we're adding an acid, right? HCl. And if it was to, well, let me put it this way. This one has the acid in it. So if we add a base, this guy gets deprotonated, therefore has a charge, therefore must be in the aqueous layer.
Hmm.
Fluorine, right? It's not going to be able to accept protons. If you accept a proton, you're going to have, or if you lose a proton, you're going to end up being charged.
So you'd be hydrophilic
Wait,
slash polar.
if you're getting a charge?
Yeah.
Yep. Yeah, because polar just means partial charge. So if you have a
Okay.
full-fledged charge, you're going to definitely be like even more than polar. But fluorine over here isn't gaining any charge. It isn't losing any charge. It's just this non-polar substance. That's why it'll have to be in the organic layer.
Histidine, lysine, arginine are all polar.
Yeah, they're
Basic.
even more so. Yeah. Like when I go over amino acids, the first thing that I mention is if they are charged or not.
Yeah, yeah.
And then I
Okay.
partial charge, right?
Okay.
Yeah.
Yeah. All right. Anyways, something a little different. This is the other question I wanted to go over.
Yep.
I don't even think we need to read the passage. It's just like a pseudo discrete.
Sure.
So
hmm?
an object with the same density as water is stationary and suspended in a container filled with fluid. A downward force is momentarily applied to the object. Assuming the water density remains constant and ignoring the effect of fluid friction, what will happen to the object immediately after this downward force is removed?
Okay. Same density as water. Okay. How would you do this? It's not this, is it?
I forget. I think. I don't know what to say.
Okay. All right, then let's see.
That's what I put. Yeah, I put D. Um. Anyways,
It has the same density as water, which is why same density as water is stationary and suspended. Or maybe I'm thinking of the object as something different. Um, Object with the same density as water is stationary and suspended in a container filled with water. A downward force is momentarily applied to the object. Let's see. Downward force is momentarily applied to the object, assuming the water density remains constant and ignoring the effects of fluid friction. What will happen to the object immediately after this downward force is removed? You remove the downward force, sink at constant velocity. Okay, so let's think about how we can set this up. We can have a force of gravity, mg. We can have a buoyant force, rho of the water, v of the object, ng. And we can set, so since we don't know if it's, okay, water density, okay, so the object here, I can rewrite as density of the object, volume of the object. I mean, up here, it should be volume of the fluid displaced. But if it's submerged, it's going to be equal to the volume of the object. So I can just do this. And the rho H2O and the rho of the object should be the same. So I'll just write rho H2O is equal to rho object, as well as V fluid displaced is equal to V of the object. All right, now Newton's second law means that we're going to sum up these two forces, but we don't know if it's going to be stationary. So we're going to solve for acceleration, I guess. So F net would be like, let's say, whatever, FG minus FB, because they're in opposite directions. And then we can have rho object v object g minus rho water v fluid displaced times g. And let's see what we can, oh, and then this could be equal to mass times acceleration here. And wait, that can't be it. Volume of the object is equal to the volume of the fluid displaced. Density of the object equals to the density of the water displaced. Um, okay. So, okay, you know what? This would equal 0, which means that the acceleration is 0. So if acceleration is 0, the velocity cannot change. Therefore, B says its velocity will change. Can't be it. Quickly stop sinking, right? If it was sinking prior and then it stops sinking, its velocity has changed, which means that there's an acceleration. That's out. Object will sink before returning to its initial position, shows a difference in velocity, which means a non-zero acceleration. So that's out. Sink with a constant velocity is the only answer choice that involves an acceleration of 0, which means a constant velocity.
How do you know that the density is equal each? Oh wait, it literally says.
Yeah.
Oh, okay, got it.
It's a good question.
Yeah. Um. Okay.
So yeah, for these types of questions with buoyant force, the biggest thing to realize is like, well, rho or density is mass over volume, right?
Mm-hmm.
So, so if you do like rho volume G, rho is mass over volume times volume, you just get mass.
Yeah.
So that's the big thing. And I've seen a lot, like they'll definitely ask you a buoyant force question. So it's good to um get like do practice for it. This was a very tricky question though, but it's a very clever question because the idea is that they're exactly all these values are the same. The density of the object is equal to the density of the water, the density of the fluid displaced is equal to the density of the object, and G is the same. So this is going to give you 0, but 0 just means, well, a 0 acceleration doesn't mean that it's not moving. It just means that, you know, uh, its velocity is not changing. And that can happen if the velocity is 0 at rest, or it can happen if the velocity is anything as long as it doesn't change. Yeah.
When an object of the same density as water is like suspended in a container, is it like how much of it is submerged? All of it?
Yeah. Yeah. Because when they're doing the whatever, the like when they say suspension, like it means that so if it was so okay, if they said floating, right? Then it would be above, right?
Yeah.
Or they can be annoying and say like it's partially submerged and partially floating.
Mm-hmm.
That's where it could be a little annoying. But if it's submerged like this, like suspended in the water is it would be if it's submerged, and whenever it's completely submerged, it's really good for us because that way the fluid displaced, because buoyant force is all about the fluid displaced. The fluid displaced, the volume of the fluid displaced must equal the volume of the object. So, so yeah, for buoyant force problems, when it's so completely submerged, it makes it very easy for us because then the volume of the fluid displaced is equal to the volume of the object. Yeah.
Okay.
Yep.
Um. Okay.
Mm-hmm.
Not this one.
Okay. This is the Doppler
Yep.
stuff. So tell me how you approach this.
Well, um, I was I was just looking for an answer that might have something to do with the difference in um velocity.
Okay. So okay, so let's see. Observer perceives the sound to be lower in frequency when the sound source is moving away from the observer. This shift in the frequency of the perceived sound occurs because, so kind of makes sense. Like if it's moving away from you, it's like a lower frequency compared to if it's moving towards you, right?
Right.
Okay. And so if we look at the choices, so A says the sound waveform velocity decreases as the distance between the source and observer increases. What are your thoughts on that?
And I don't think the thing is like with Doppler effect, it doesn't have to do with anything with has nothing to do with distance, or it
Okay.
doesn't.
Well, so I guess they're just saying, well, I guess that if this is the sound source and then this is the person and the distance increases, it just means that they're going away from each other, right?
Hmm.
So I think the distance part is fine, but the sound velocity,
So that would increase, right?
I think the sound velocity is the thing that won't change. Like the source, like the speed of sound, basically. Well, maybe you're thinking because there's speed of sound and then there's speed of the thing that's making the sound, right?
Interesting. Okay, so because what I was thinking is V equals F times wavelength,
Okay.
but so I mean it's like if frequencies change and velocity doesn't change.
Yeah. So the thing with the Doppler effect is that it's a perceived change in frequency.
Hmm.
In actuality, the frequency is not changing. Like if you had like a siren with whatever pitch, um that pitch doesn't change, but if it's driving towards you, you observe a pitch that would be higher in frequency because it's coming towards you.
Right.
When it as it moves away from you, like and when it's right in front of you, that's the actual frequency or pitch of it. But then as it moves away, the perceived frequency or pitch would be lower. So it's all about like the observer and the source of sound. Are they, going towards each other or away from each other? If it's either of those things, Doppler effect happens. If they're stationary, it doesn't really happen. So, what are your thoughts?
What I'm trying to understand is so what is there's the sound itself, the velocity doesn't change, right?
Yeah, because like there's the speed of sound and there's the speed of the source of the sound.
Oh, okay.
Like,
Right.
let's say this object
Yeah.
is releasing sound waves in a circle like this. But let's say it starts moving to the right really fast, it'll kind of like these sound waves will kind of bunch up. It's a bad drawing, but they'll bunch up around in the front of it.
Mm, so the actual velocity of that sound doesn't change, but the fact that it's like moving faster, that's the velocity that you're referring to. Yeah,
Yeah.
because the equation has like those three different v values.
Uh-huh.
Okay. Yes, then A would automatically, right? It's out because they're saying there's a change in the sound. Okay.
Yep. So it's
So it's not a sound waveforms are reflected off of environmental objects nearby. And I just don't think that really has to do much with the problem. Like I remember I crossed that out right away.
okay.
Like um C was the right answer. And then D, the sound wave intensity decreases as the distance between the source and observer increases. Look, intensity is power over area, is energy over time over area.
Yeah, yeah. And the big thing about intensity is that they like to trick you a lot, especially when we talk about photons. We're talking about sound here, but with photons, you be cautious of whenever we're talking about intensity. But intensity essentially is, think of it as the number of sound waves, and it corresponds with loudness.
Intensity and loudness.
Yeah.
Intensity is the same as loudness.
Uh intensity, I would think of as the number of sound waves for like, so intensity in light is the number of photons, right? And in,
Intensity is number of photons.
yeah, it for light, yeah. And that's something
Okay.
that's a big deal because photon energy of a photon is based on its frequency, but a lot of times they'll try to trick you by asking like something about like let's say a photon doesn't get absorbed because it doesn't have enough energy, so they could say what can help, and the choice could be like increasing the intensity, but that won't help because you're not increasing the energy, you're increasing the number of photons, which corresponds with brightness. And then for sound, think about it like this. Think about like you're at a whatever. What sport do you like sports? Like what sport do you like?
Yeah. I mean,
You're
football, American football.
you're in a football game, you're yelling,
Yeah.
and that's gonna be a certain intensity, which we can translate into loudness, like decibels. And then let's say
Mm-hmm.
that 100 of you are yelling in that same loudness, but just
Uh-huh.
100 of you. So that means that we're gonna get 100 more, whatever, or 99 more sound waves. So the intensity is going to increase, meaning that the loudness increases. But you're also absolutely correct in intensity being power over area, because like in the summertime, do you think we're closer to the moon or further from the moon? Sorry, closer to the sun or further from the sun?
Um, Closer. Days are longer.
We're actually further,
Okay.
but I mean, like obviously that's not intuitive, but during the day, when is it hottest?
In the
7
middle.
7 a.m., noon,
Noon.
p.m. Noon, because that's when the sun is directly above you and all of its rays go down across a small area. If it's going from the side, it's at an oblique angle, so the intensity decreases because it's at a larger area. So, yeah. So for this one, we are essentially if the source of the sound is moving away from the observer, the observer perceives the sound as having a lower frequency, aka a lower pitch.
Okay, because these terms are all jumbled up in my head.
Yep.
Frequencies, pitch.
For sound, yeah. So let's think about it like this, right? This might help. So for light, particularly visible light, because when we talk about intensity or Doppler effect with light, we're talking about visible light. So, uh, so for instance, let's say we're looking at through a telescope and we see some, or let's see, we see some planet that is supposed to be blue, okay, but it looks red. That means that its frequency is going like down, which means its
Yep.
wavelength is going up, and we say that that's a red shift, and that's how we can say that the universe is expanding because it's moving away from us.
Hmm.
And same thing, and that's just the Doppler effect with light. The Doppler effect with sound, instead of the wavelength being of a certain color, the wavelength would be, you know, more so related to pitch. I mean, obviously, frequency, both of them, like high frequency is a high pitch, um, but it's the same kind of thing. So just yeah, so just equate like frequency for sound is pitch.
Okay, so I can make an knocking card saying high frequency equals high pitch.
High frequency, high pitch for sound.
High for sound.
Yep.
Okay.
Yeah.
Now intensity is the number of photons of light.
Hmm.
If you increase the intensity, you're increasing the number of photons, but are you increasing the energy?
No.
No.
Yeah. That's something that they love to test.
So the energy is not being affected.
Correct.
Okay. Um, how is amplitude related to brightness of light and frequency and pitch and yeah,
Oh, amplitude?
amplitude. Yeah, does that mean brighter light, higher
Yeah,
amplitude?
yeah. Yeah, that's a good question. Yeah, it does. You usually you're like I haven't really seen that many questions about um amplitude, but yeah, that would be something like, brightness or intensity.
Okay. So going back to this question.
Yeah, I just sent an email just to get it straight. Intensity for light, number of photons, which corresponds to brightness. Intensity for sound, number of sound waves, which corresponds to loudness. Intensity, unit, power over area. Intensity is not energy.
Great, thank you.
That in. Yep.
Um,
Yeah. So,
wait, so increase in frequency
yep.
in terms of light, increase in frequency means an increase in energy of photons,
Um,
right? The equation.
yeah, but we want to make sure that we understand that the Doppler effect is not causing really an increase or a change in frequency. It's a perceived frequency,
Hmm.
right? Because the sound object or the light object is at whatever volume it's in, right? Like that doesn't change. But if it's going towards you, you perceive it as being of a higher pitch or frequency, but that's just what you perceive. It's not changing the actual frequency of light itself.
Okay. Both the velocity of the sound and the frequency of The frequency and the velocity are both not changed.
Or yeah, because
The sound.
yeah, like the the formula has the V has the what was it again? It was like V plus V naught over V minus Vs times the
Hmm.
original frequency gives you the observed frequency. And so um, the regular V here is the sound wave velocity, which by the way is around 330 meters per second. It's basically 1 millionth of the speed of sound. Um, V naught here is the, or maybe it's not V naught, maybe it's just V's O because it's the velocity of the observer. Vs is the velocity of the source, and F is just the actual frequency, and F with like this symbol here is the observed um, frequency.
Okay, so now, wait, how about wavelength? Nothing, wavelength also stays constant?
Um, there could be a perceived change in wavelength. That's kind of easier for us to kind of think about when it comes to light, but yeah, their frequency and wavelength will be inversely proportional. It's just that when we talk about different colors of light, we typically talk about it as different wavelengths of light. But for sound, we typically talk about it as different frequencies. Um, so so yeah, it's just like by convention for Doppler, we think about it in terms of frequency. Um, yeah.
Okay, so D, sound wave intensity decreases as the distance between the source and observer increases.
Hmm.
And so, um, how does intensity relate to light? Wait, I mean, sorry, not light, sound.
Hmm.
Intensity, yeah.
Pretty much same type of thing. You have a number of sound waves, and that correlates with loudness, right? Because if you think about decibels, it's 10 times the log of the intensity over the threshold intensity. So right there, we could see that intensity is contributes to loudness. And the Doppler effect involves a shift in the frequency of the perceived frequency. So if D was the case, that would mean something with loudness. If the intensity decreases, that means that the loudness decreases.
But the loudness is not changing.
Yeah, not really. I mean, you know, obviously an ambulance that you're right in front of is going to be louder than it's like when it's down the block or whatever. But the Doppler effect is not concerned with intensity because I guess you could say that for anything. Anything, any sound, if you're closer to it, will be louder than if you're further from it, right? So
Hmm.
while that might be something that's true, it's not what the Doppler effect is. And so the Doppler effect is what we're essentially seeing in terms of perceived pitch of something moving towards you, moving away from you. But there has to be things that are moving. In this diagram here, I drew like the source moving away and the person moving away, but the person could be stationary as long as one of these things are moving.
Hmm. So why is it C then?
Let's see. Successive sound waveforms are emitted further away from the observer. Yep. Like, like kind of what I drew here with the circles. Like, think of each circle. Maybe I could find a good. I have an idea. All right, in the chat, I'm gonna put in a GIF of this is
Mm-hmm.
a sonic boom. Okay. Now,
Mm-hmm.
are you able to see it?
Yep.
Okay. So this is showing you, okay, so like you see how the let's see if I can kind of do this. Okay. So like let's say this is a stationary object, it's gonna like release sound like whoops in like these concentric.
Yeah, yeah, yeah. Okay.
You know, it's not as perfect as I want it to be, but if it moves
Yep.
in any direction, so it kind of looks like if it's moving, you know, in this direction here, it,
Mm-hmm.
the sound waves that it releases bunch up since it's moving in that direction.
Right.
As opposed to if it was just not moving, it would be like it's hard for me to draw these like
I know what you're getting at, yeah.
yeah, something like that. So
Mm-hmm.
yeah, and then the GIF that I put in the chat is kind of like a an extreme case here, and that's when the red object is the one that's releasing sound, so it's the source of the sound, and it's moving to the right, and you can see that as it moves to the right, the oh, these are called the waveforms, by the way. The waveforms or the wave fronts, like you know, this and stuff, they start to bunch up. Um, and this is if it's moving like too much in one direction, but you know, this one is if it's moving away, so the what so it bunches up less so. But that's why, you know, so in the GIF that I sent, that's what um that's a sonic boom. Basically, when you have the actual, you know, thing that's creating the sound going faster than the sound that it's releasing. So essentially, you can't hear it until it's already past you.
But how would that look, honestly? I mean, I know you're having difficulty drawing, but like drawing it. How would it look like? Successive sound waves are emitted further away from the observer. So,
Huh? Yeah. So
uh-huh.
if we have, so they're saying that the dude observes a lower frequency sound. So that means that the source of the sound, well, it tells us even, is moving away from the observer. So if this is the observer, and this is the thing that's releasing the sound, this would be what it looks like if it was not moving. But if it
Yeah.
starts moving this way, it'll start to like bunch up here. And as it continues to move away from the observer, each new sound waveform, aka each new like, you know, circle, is emitted further away from the observer. And if it's emitted further away from the observer, that means, you know, it's moving away from the observer. And so the observer perceives a frequency that's lower than if it was moving towards it.
How do waveforms connect to frequency again?
Oh, so
Just because
yeah,
you need to know that?
so the waveform is just like each one, I guess, is like let's say like a pulse of sound
Yeah.
like that. Um, and if it's moving in one direction, like in a direction, let's say that's away from the observer, that means that there's more distance between that source of sound and that observer. So it's going to like just like it bunches up in the direction that it's going, the direction that it's moving away from, the waveforms are more separated, and each new waveform is further from that observer.
But we said distance isn't. I mean, that's like the main. That's not the main focus of Doppler, right?
So the distance, so the way that they're wording like the distance for like this and this over here, like is a consequence of that change in velocity. In order for the source of the sound to move away from the observer, the distance between that source of sound and the observer must be increasing.
Mm-hmm.
So if something's moving away from you, the distance between you and that thing is increasing. So that's
Okay.
how, yeah. Because I think what you're saying is like distance is not what determines the stuff in the Doppler effect, but you can think of distance not like explicitly as something that you put in the equation, but a consequence of the velocity changes in the equation. Yeah. So maybe this could help. Let's say that here, this is a sound wave, and it's going this way at the speed of sound, 330 meters per second. And this is a certain distance, so it'll take a certain amount of time to reach the observer. And then it travels a further distance and generates another sound, which will still be traveling at the speed of sound of 330 meters per second. But this will take longer because it's further. It'll take longer for it to reach the observer. And this will just happen. And that means that the wave forms are each new waveform is further away. And so eventually when it reaches the observer, it's going to sound like it's a lower pitched sound.
Mm-hmm. Okay.
Mhm. Yeah. And I put in like a picture of a jet
Yeah.
that's past the speed of sound. So you can see that there's this huge, like that little kind of funnel behind it is all of the bunched up waves.
Mm-hmm.
Um and it also means that it's like if it flew right by you, you can only hear it after it's done that because it's supersonic.
Okay.
Yeah. Here, I found another one. This might be better. Yeah, try the one that I just sent.
It only lets me download it.
Yeah.
Yeah. No, yeah, I understand. Okay.
Mhm. Yeah.
Okay.
So like you see how the distance between the stationary observer and the moving sound source is going down.
Yeah.
And so in our example, it would just be moving away, and that would mean that the distance between the sound source and the observer would be getting larger.
Okay.
Yep.
So as it's moving away, the waveforms, yeah, I mean, because it's moving away, the distance is increasing, and that means the waveforms are further away.
Mhm. Yep.
the intensity.
Mm-hmm.
Um, D was wrong. Why again? Sorry. D is intensity. Yeah, so it's inversely related distance. Wait, increasing unrelated to the motion of the source and observer.
Yeah, so that's what I was saying. Like that might be a true statement because intensity is related to loudness. And of course, if something's like the sound source is right in front of you, it'll it'll be louder than if it's moving away from you or even towards you. So D might be a true statement, but it's not explaining the Doppler shift, which is that shift in frequency.
Okay.
Yep.
Last questions. This one.
All right. So let's see. It's a inhibitor question. So like usual, I'll ask you like, okay, what how what's your approach here?
Honestly, I was like a little confused by the diagram. Um,
So let's see what the top says. It says shows the effect of an inhibitor on an enzyme when the enzyme and inhibitor were pre-incubated prior to the addition of the substrate, and then when no pre-incubation happened. Um, Constant amounts of enzyme and initial substrate concentration were used for each test. Um, Based on the graph, which of the following statements is true? So we have the percent activity, y-axis, inhibitor concentration, x-axis. No pre-incubation curve seems to be to the right, a rightward shift compared to the 30-minute pre-incubation. What's the significance of a rightward shift?
that's the thing. I wasn't really sure. I mean, it has to do something with, I guess, KM.
So let's think about, because typically, sure, we would see like the x-axis be the substrate concentration, in which case we can figure out Km, but the x-axis is really just giving us the inhibitor concentration. But if you think about, for instance, so this is going to be true for all kind of graphs like this. A good example is like the Bohr effect, but look at it here, I'll show you. Look at it this way, right? So let's say that in order to get, so let's say with the pre-incubation, in order to get 50% activity, you need like what? This is like some like weird logarithmic thing, but let's say this is like 50 like x-axis inhibitor concentration, right?
Hmm.
So okay, so we need some value like there. Now let's think about where the for 50% activity for the no pre-incubation like condition. You need 100 of that inhibitor, right?
Hmm.
So so a rightward shift shows that in order to achieve that same percent activity, you require more of the inhibitor.
Yeah.
Okay. So that's how to evaluate things like this with, um, like a shift. It's like exactly like the hemoglobin, whatever, or
Yeah.
if it's moving to the right, it's not as effective, because it needs more inhibitor to reach that same level of activity. So right away, that's how we can kind of compare these two. Clearly, it seems like pre-incubation, right, uh, helps the inhibitor inhibit things, right?
Hmm.
Okay. Now, okay, they are They're using constant amounts of enzyme and initial substrate concentration. Um, okay. I I was gonna say I don't really like that, but because Michaelis-Menten conditions are where the substrate concentration is significantly higher than the enzyme concentration, but it's okay. Let's see what we can do. A, reversibly. B, inhibitor. All right, what do you think about B?
That's I was gonna say it's right away wrong because it's less effective.
Yeah, good. Um, then C is the opposite of A, and then D. What is D saying?
Mm, don't know.
So, uh, let's see. So, what type of okay, so forms weak bonds with active site residues makes me think competitive inhibition. Um, because a competitive inhibitor competes for the active site. So let's see. No precipitation. Oh, sorry. No pre-incubation. 30-minute pre-incubation. I mean, A and C are opposites. D, inhibitor forms weak bonds with active site residues. Hmm. Okay. What would you think between A, C, and
I just wasn't sure. Like, I mean, I was between A and C. Um,
so
I was not sure.
you didn't like D?
I didn't like D because A and C are more likely to be the correct answer because they're opposites. I
Uh-huh.
didn't know why D was wrong.
Okay.
Um, you said D refers to competitive inhibition. Um, yeah. I mean, I wasn't sure. I don't know how to like deduce whether or not it's reversible.
Yeah. Hmm. Okay. So I know for competitive inhibition that it can be overcome by increasing the amount of substrate concentration. So if that means the same thing as decreasing the amount of inhibitor concentration, maybe that can be something related, but I don't know how I would be able to tell if it is reversible or irreversible. My guess would be that if it was irreversible, well, if it was irreversible, after it binds, it should be done. Like I would imagine that it would look not like sigmoidal, perhaps. Inhibitor concentration increases, pre-incubation, effective an inhibitor on enzyme activity, pre-incubated prior to the addition of substrate. Okay. You're saying it's not D?
It's not D.
Okay, so then it has to be A or C then, right?
Yeah.
Okay, okay. Um, I guess I'll go with
I mean, I could just give you the answer.
maybe A.
That's what I put it. See,
Damn it. Okay.
I have no idea. Like,
Yeah.
honestly, it only. I mean, not only 51% got it right, so I was like pretty surprised that many people got it right.
Yeah.
It talks about it being irreversible, and that means it forms covalent bonds. Yes, that I know, but um, I guess talking about time and I mean, that's why I asked you. I don't really understand this.
Okay. Irreversible covalent bonds to the enzyme. Once it cannot be displaced by any amount of substrate. Pre-incubation, more time for the covalent bonds to occur. Therefore, it can increase the level of inhibition because more enzymes are inactivated. However, reversible and non-covalently, okay, binding interactions are generally much faster. Okay. Um, Reversible, same effect, whether, okay. So apparently, irreversible would mean that, well, when the inhibitor binds to the enzyme, that it can't, well, I guess it kind of makes sense then. If it's irreversible, the enzyme binds to the enzyme, doesn't change it. Doesn't, I mean, when I say doesn't change it, I mean cannot be undone, right? And reversible can be undone, right? And then pre-incubation means that if it's irreversible, then it's not going to unbind. So let me see. Additional time, okay, reversible, same effect. Okay, so reversible, irreversible, pre-incubation equals, not pre-incubation. Pre-incubation greater than not pre-incubation. So that means that if it's reversible, oh yeah, interesting. Increased inhibition. Wait, no pre-incubation, 30-minute pre-incubation. Yeah, I think I also was thinking of it too much in terms of left to right
Hmm.
because that's what I usually see, but it actually should be right to left because the no pre-incubation part is to the right. So if there's no pre-incubation happening, uh the inhibitor is not very good at stopping that activity compared to if it did have pre-incubation. So pre-incubation means that you're letting the enzyme and the inhibitor interact before you add the substrate. And so if you let that happen, right, that means that in the pre-incubation condition, you should have more inhibition compared to the no pre-incubation step. Because, yeah, so basically, irreversible pre-incubation step, enzyme binds to the inhibitor and it messes it up. Whereas if it's reversible, whether it's pre-incubated or not, you should see similar results because it can be reversible.
Hmm.
Yeah. So that's that's a tough question here. But I think the best way to view it is that if we have the same or similar values for if we pre-incubate compared to no pre-incubation, that should be reversible. But if we have different values, that would mean irreversible.
I never really heard of incubation though, like as a term.
But that's what they're gonna do. I mean, likely not on an AMC test, but UWorld, right? I guess this is all UWorld.
Yeah.
Yeah, this stuff is always going to be more complicated, but in a good way. So now we know,
Yeah.
yeah, now we know that if there's like if both of these were if both of the lines were really like close to each other, reversible. If they're far from each other, irreversible. And then pre-incubation is just according to the question stem, the enzyme in the presence of an inhibitor. And the reason that it was kind of seemed weird at first is because we're used to seeing enzymes in the presence of a substrate, and then you can add an inhibitor. This question stem involves an enzyme with an inhibitor, and then you add the substrate. So we add the inhibitor
Hmm.
first. So there you go.
Okay. Got it.
And then I guess the extra stuff that they're writing here, you can kind of add to like an Anki card or something. Particularly like irreversible ones forming covalent bonds, reversible ones, you know,
Yeah.
non-covalent. Also, that the reversible ones uh bind bind much faster.
Okay.
Yeah. Mhm.
They bind much faster to the enzyme.
Yes. Yeah.
Yeah. Okay. All right. That's all. Um. Yeah.
Did that question that genetics question make sense? Kind of.
It didn't fully. It didn't fully
Hmm.
settle. Like
All
I
right.
saw what you sent me, but
Yeah. Yeah. There's like little
um.
text in that. So I'll like try to make like a little short video that can go over it.
Okay.
Just wanted to send well, okay.
Sorry. What'd you say?
Oh no, I just want there was like a question that I wanted to send you, but I can't find it. But it's like it's a you'll probably see it in New World. It's like a something with oh, I got it. It's here. It's a buoyant force thing. Put it in the chat. But yeah, okay, okay. So yeah. Oh, and then yeah, check the I sent a picture of like my notes for separation
Mm-hmm. Yeah, yeah, yeah.
stuff.
Thank you. I saw.
Yep. And so tomorrow you're taking your next blueprint test, and good luck on that. And yeah, just remember it's much harder than AMC stuff, as well as the UWorld stuff that you've been showing me. So don't
Yeah.
feel too bad about that. But I wonder when you're gonna start. I forgot when you were gonna start like the AMC stuff.
Yes, I was trying to do the AMC stuff like one passage every so often because I didn't want to do a lot of it at once because I want to thoroughly like review every passage when I do it.
Yeah.
And I also don't go over it with you
Uh-huh.
because like I was looking through YouTube videos and a lot of them are like the AMC stuff, you know? So it's like I can just watch over that, like let's be real. And like a lot of the UO problems, you know, a lot of them are really unique and they're hard, and so that's why I choose to go over those with you.
Yep.
But I feel like this is a conversation to be had maybe after I take this next exam because I also wanted to just like talk to you in like the grand scheme of things. Like I just don't know if I'll be able to make it in time for September.
Yeah.
But
So I'm looking at your thing now, and you're gonna take your AMC test on the 26th of this month. Um, and if you want to like if that's too late or whatever, we can maybe do it sooner. But the idea is that like the blueprint tests are just going to be really hard and deflated, and the idea or the goal is that when you do the AMC test to see a score jump, if we don't see that, then yeah, maybe we can talk about
Yep.
something else, But
Mm-hmm.
I think that doing the UWorld, doing the Blueprint really tough tests and doing the UWorld really tough stuff, uh, is putting you in a great position for when you do take the AMC test. Um, but yeah.
Yeah. I mean, I have until August 6th. That's the last day where I can like at least, make some money back in terms of like
Oh,
canceling and then rescheduling, whatever. So we
yeah.
have until then. But I'm trying to put my best foot forward no matter what.
Yep.
So yeah. And the last thing, tomorrow, I ran out of those like Jack Weston practice exams that are like insanely hard.
Mhm.
What
Oh,
should I do?
what
Just
you're using.
create,
Yeah.
yeah, because
That's
they used to have a lot more available. Now there's only
yeah.
two.
Yeah, yeah. Yeah, I think because they released like a full length like exam. But yeah, you can kind of just use like the Q bank, I think. Like,
That's what I was gonna tell you. Should I do that? Yeah, I was thinking
yeah,
about
you'd hit like
that.
the
Okay.
style passages, hit unseen, I guess, cars and
Yeah.
the 1800, 11 of them. Uh,
Okay.
and then for like the sections, like maybe select all of them to give you like a good
Yeah, yeah, of course.
yeah, so you can use that. And when you're reviewing, compare your main idea with the main idea uh in the solution. But yeah, I think that what you're doing is putting you in a good position for all this stuff. Cars is gonna be tough, but
Yeah.
to get through it. Um, you know, just try to trick yourself into being like interested. Um,
Yeah.
Easier said than done.
I mean, at this point,
Mhm.
I mean, I'm just hoping for like a 125.